Welcome to this explainer. Today, we're unpacking a truly critical networking concept, flow control. You know, in the world of cloud infrastructure and high-speed computing, flow control is absolutely the unsung hero. It's the literal glue preventing modern data centers and global networks from just collapsing under their own weight. So, we're going to dive deep into this mechanism and see exactly how it acts as the ultimate traffic management system. It's what prevents digital disaster and ensures those massive multi-gigabit pipes process information flawlessly.
But before we get into the heavy technical protocols, ask yourself this. What actually happens to your data when a sender talks way faster than a receiver can listen? Just imagine someone reading a really complex phone number to you at 1,000,000 miles an hour. You'd inevitably drop a few digits, right? Well, in computer networking, the exact same thing happens, but man, the stakes are so much higher. Picture a massive 10 gigabit per second enterprise server just blasting a payload down to a constrained edge device, or maybe a legacy 1 gigabit switch. The receiving hardware literally cannot process the electrical signals fast enough. So without a robust mechanism to regulate that conversation, the fast device will absolutely flood the slower one. And that imbalance, it leads to dropped packets, corrupted files, basically a total breakdown of communication. We absolutely need a rigorous, mathematical way to manage that pace.
So, to get our heads around this, here's our roadmap for today. First, we'll look at the core purpose of flow control. Second, we'll explore the 5 main flow control mechanisms. Third, we'll see how flow control works in TCP. And finally, we'll wrap up with Ethernet and the data link layer. Let's get into it.
Starting off with Section 1, the purpose of flow control, and exactly why pacing matters so much.
At its very core, flow control is a critical pacing mechanism. It's designed to ensure that data transmission between devices is both efficient and reliable, completely preventing the receiver from being overwhelmed. Think of it as the invisible hand guiding the speed of your data. And preventing data loss at this level is incredibly critical, mainly because of the unseen costs of a failure. You see, when packets are dropped, it isn't just missing data. The receiver's CPU has to actually realize there's a gap, issue a retransmission request, and then the sender has to go locate that specific packet in its memory and send the whole thing all over again. It's a massive pain. It creates huge CPU overhead and cascading network delays. Flow control steps in and stops that chain reaction dead in its tracks.
So we really rely on flow control for 3 highly critical reasons. First up is preventing data loss, which saves us from all that processing overhead we just talked about. Second is synchronization. Think about a CPU's interrupt requests. When the sending and receiving speeds are perfectly matched, the receiving processor can efficiently schedule its cycles without being violently interrupted by an overwhelming, unpredictable flood of sudden data bursts. It keeps things smooth. And third, optimizing performance. By avoiding network congestion, we stop localized issues from spreading, because without flow control, a tiny bottleneck at a single switch can quickly trigger queue buildups upstream, literally turning a minor switch issue into a massive network-wide cascading failure. Nobody wants that.
Moving right along to Section 2, the 5 flow control mechanisms. Let's open up the toolbox and see what we're working with. Network architecture essentially utilizes 5 distinct mechanisms to maintain this delicate balance. First, buffering provides temporary memory storage right on the hardware itself. It basically creates a waiting room for data. Then we have windowing, which establishes a strict, negotiated limit on exactly how much unacknowledged data can be in transit at any one time. It sets a baseline capacity. The sliding window protocol takes that idea a step further, creating a dynamic, moving baseline that adjusts mathematically on the fly based on real-time network conditions. Next is explicit signaling. This one completely removes any assumptions from the process. It relies on highly specific, direct, stop-and-go messages between the devices. And finally, pause frames. These are literal physical layer hardware commands, commonly deployed in Ethernet environments, used to instantly and forcefully halt transmission on a specific cable link. Each of these tools serves a very unique architectural purpose.
Let's look closer at buffering. It acts as that critical temporary waiting room for incoming data, buying the receiver some precious time to process things without forcing the sender to just abruptly halt. The data simply sits safely in the hardware buffer until the receiving device's processor is actually ready to handle it. But here's the catch. What happens when that buffer inevitably fills up to its maximum capacity? Well, it leads to a condition known as buffer overflow, or tail drop. This is where any new incoming packets are indiscriminately discarded simply because there is literally zero physical memory left to hold them. This catastrophic dropping is exactly why buffering alone is never going to be enough. We need active signaling mechanisms to step in and stop the flow before a tail drop even has the chance to occur.
To prevent those buffers from overflowing, we bring in explicit signaling. This is a highly direct approach where the receiver explicitly communicates its readiness to accept more data. A classic real-world example of this is the X-on and X-off protocol used in software flow control. If a receiver's buffer is nearing maximum capacity, it proactively transmits an X-off character which literally commands the sender to pause. Just stop right there. Then, once the receiver clears its backlog and frees up some memory, it sends an X-on character, signaling that the floodgates can safely open up again. It totally removes all the guesswork and provides absolute certainty for the connection.
All right, let's jump into Section 3, Flow Control in TCP, or Transmission Control Protocol. Let's see this in action.
TCP uses a beautifully dynamic, continuous conversation between a server and a client to maintain optimal flow. In Step 1, the receiver actively advertises its window size, dictating the exact byte count it can currently accept. In Step 2, once that data arrives safely, the receiver fires back an acknowledgment, or ACK. But Step 3 is where the brilliant sliding window algorithm really takes over. This window isn't static. It constantly breathes. If network latency is low and ACKs are returning rapidly, the sender dynamically expands the window, pumping way more unacknowledged packets into flight to maximize throughput. But if an ACK goes missing or takes just a little too long to arrive, the sender interprets this as network congestion. It immediately shrinks the window, choking back its transmission rate to give the network time to clear out. So you get maximum speed when the path is clear and immediate throttling the very millisecond congestion is detected.
Finally, Section 4, Ethernet and the Data Link Layer. Let's talk about shared media flow. Way down at the data link layer, Ethernet relies on a highly physical concept called backpressure. If an Ethernet switch port gets flooded with a massive microburst of traffic, it exercises backpressure by transmitting an IEEE 802.3x pause frame right back down the wire. This tiny, yet incredibly powerful frame tells the upstream sender to completely halt transmission for a precisely specified duration, usually measured in microseconds. It's essentially the network hardware literally throwing its hands up and saying, "Whoa, hold on, let me process this queue before you send me even one more bit." Now, because Ethernet was traditionally a shared medium, devices historically relied on CSMA/CD. That stands for Carrier Sense Multiple Access with Collision Detection. Now, I know what you're thinking. In modern cloud infrastructure with fully switched full duplex environments, physical collisions aren't really the daily operational issue they used to be, right? The lines are dedicated. However, understanding CSMA/CD is absolutely critical because it's the foundational bedrock of how shared media originally organized flow. Devices had to physically listen to the copper wire, that's the carrier sense, and only transmit if it was completely silent. If a collision occurred, they exponentially backed off. And while you might not be troubleshooting a physical copper collision today, these exact same collision avoidance principles fundamentally power modern wireless networks through protocols like CSMA/CA, ensuring our airwaves don't just become an unreadable mess of overlapping radio signals. So why does all this matter for you? Well, when you're engineering cloud architecture or troubleshooting a complex distributed application, misconfigured flow control can easily masquerade as application lag, mysterious database timeouts, or even spontaneous server failure. Often, the computing infrastructure is actually perfectly fine, but the fundamental traffic management is secretly failing under the hood. So as you take these networking fundamentals back to your own projects, I want to leave you with this crucial thought to consider for every single connection you build. Is your data flowing or is it overflowing? Thank you so much for joining me for this explainer. Keep building, keep learning, and I'll catch you next time.